Hello, today we're going to do 2.5 on reasoning with using properties from algebra. So first, let's look at some key properties. So first, as everyone knows, there's additional property, which is pretty simple, right? A is B, then A plus C is equal to B plus C. It's pretty simple. And the subtraction property is basically just subtracting like digits, and multiplication property is multiplying, division is division, and substitution is replacing. Maybe if A is equal to B, you can substitute B for A because they're the same value, and this is really pretty straightforward. I think something we should know is how to go over kind of the proof aspect. And here, if you see, even if you're trying to prove something like as simple as this kind of algebraic equation, you know this because it's given the problem. But when you add plus 3x, that would be the additional property of equality, not congruence, because it's not this, right? So we have to know that when we add to solve this problem, it's the additional property of equality. And when you're basically simplifying, it's just simplify. The next step would be just subtracting, because you're subtracting 5 from 20, which gets 15. And when you are trying to get your final answer and isolate the x, you divide 5 to the other side, which gives the final answer of 3 using the division property of equality. Next is the distributive property, and it's basically saying if a times b plus c is here, then it would be a plus b. It would be equal to a plus b. A b plus ac is equal to a parenthesis plus b plus c. This is also pretty straightforward distributing. I think, yeah, it's similar to the proof earlier. So you just have to know the given. And here you're using the distributive property, subtraction property of equality, division property of equality. Basically, when you're dividing, you write division property of equality, subtracting, subtraction property, so on and so forth. Now, these are some key properties that come a lot, not just in algebraic proofs, but in geometric proofs when you maybe prove like congruence of triangles and whatnot. So they're very, very important to note. So first, the reflexive property of equality is basically like saying A is A, right? So basically, it's something like maybe angle ABC is equal to angle CBA would be the congruence property of equality, because it's essentially the same thing. Sorry, well, reflexive property of equality, but in that case, that would be congruence. But remember, equality is just equality, and congruence is just this. So there isn't like a huge major difference. There's only in terms of notation, there's a difference. And next is the symmetric property of equality, and it's basically saying if A is equal to B, then B is equal to C. So if you're saying maybe this, like, I don't know, something like, then basically the opposite is also the same. True. That's basically what the symmetric property of equality is stating. Transitive is, you can kind of think it like a link. So you're linking kind of two different things. So something like, if there was an equation like A is equal to B and C is equal to D, right? Like something like A is equal to B, and let's say B is equal to C, then we can make the link because B is equal as A equals C. And that's basically the transitive property of equality at its core. This is a pretty, yes, this one's a pretty simple proof because you're just using the given, angle addition postulate, substitution property, angle addition, transitive. But if you look at these kind of forms of equality, because we know what's given, and when we're adding, it's the segment addition postulate, and we also add here, also the segment addition postulate, and we can know that when you're adding BC to both sides, it's addition property, and that's the property used here. And basically, when you're substituting each value, then you get AC is equal to BD. So basically, that's the essence of 2.5. I think these kind of problems are like these problems are pretty straightforward. It'll be just good to look at maybe a couple proofs if there are any. I don't know, if you look at just something like this. So just dealing at the table. Here, given, I don't know what explanation here there is because it's given by problem. Here, we're just looking at copy and complete, show that angle measure M is equal to angle measure 2 and 3 is equal to each other. That's basically what we're trying to show. And here first we're showing EHF is equal to FGHF, and that would be because it's pretty clear they're both right angles and they're obviously equal. And here you're just adding the measure of adjacent angles, and this would be the angle addition postulate. And here basically you're just kind of substituting, should I say? So you're basically substitution. Because we know that these two, and then here you're substituting measuring angle 1 for 4, so something like measuring. And because you're here subtract, and this would probably be substitution property of equality, and as a result you get this value, and this is pretty much done by subtracting measure. So basically this is how the proof would go. I think it's pretty straightforward here, and we can just go on to next proof statements about segments and angles. So when it comes to proofs, there's two main proofs. Well, first of all, to note that proof is a logical argument that shows a statement is true, and you can do it in many ways. And a way of doing it is a two-column proof, and it's basically what we did earlier, so something like this, and you could say like, oops, something, I don't know. So, and this is like a given statement and given, and so on and so forth. So basically, it's just a column like you see here, and that's basically you just write a column saying statements, reasons, and it'll probably give you a given and prove, and it'll often the diagram as well. So look at some theorems, right? Essentially, what a theorem is, you need to kind of prove the statement. It's not something that's just given like a postulate. And proofs can include like definition, properties, and just really a lot of things. But I feel like some key theorems here. First, look at the congruence of segments. So basically, if any segment, as we learned, like the reflexive property of congruence would be it's equal to itself. Symmetric is the other way around is also equal. Transitive is kind of making a link, like these two are congruent because of the CD. The congruence of angles is also similar. Reflexive angle A is obviously equal to itself. Angle A is equal to B, then angle B is equal to also angle A, vice versa. And transitive is once again a link, right? So these are just basically congruence theorems that you must prove, and it's not a postulate because it's not so obvious, right? These are just, I think you can just deal with these proofs by looking at them. And I think you guys probably know how to write a two-column proof. It's up there if you need it, and it's pretty straightforward, to be honest. So just before we move on, let's take a look at some number 3 and 4. Just A, B, B, C. So if you're given these two statements, and here the segment addition postulate states AC is equal to AB plus BC, which is also pretty straightforward. And because you're substituting 5 for the value, the length of AB, and 6 for PC, you're doing the substitution property of equality. And the last step is you're just adding these two, and that would be simplification, giving you AC is equal to 11. Looking at number 4, which property losses is the reason for the last step in the proof? So because we know these given statements and we're trying to prove that they're equal, because we know that measure 2 is also equal to 59. Sorry, measure 1 is also equal to 59. You're using the substitution property. Or to be more straightforward, it would be using the reflexive property because you're showing a relationship between the two with a link as seen above. And I think that's it. So great job so far. And now let's go to our last section, improving angle pair relationships. So here's some common theorems. So the right angles congruence theorem. It just says that all right angles are congruent to each other, which is pretty straightforward because 90 degrees is equal to 90 degrees. There's a proof using it. When you're trying to show like very obvious things relating right triangles, like angles, you can always use the definition of a right angle because it's like common, it's literally what a right angle is. And these proofs are pretty straightforward. So if you look at two more theorems, there's the congruent supplements theorem and then the congruent complements theorem. You can recall that supplements calls to 100, means like 180 degrees. Oh, sorry, 360 degrees total. So you can recall complementary is always something like 90. Here is 180, so you can kind of use that to know that if two angles are supplementary to the same angle, then they are congruent. And here, if they're complementary to the same angle, then they're also congruent. These are some proofs. Again, two more postulates, and remember this one especially because this one comes out a lot. Well, this one also does. So these two postulates are really important to remember. First, the linear pair postulate is if two angles form a linear pair, then they are supplementary and thus equal to 180 degrees, as you can see in this diagram. Vertical angles congruence theorem, you can always think this way and this way. If they look at each other at opposite directions, then they are congruent. So like here would be, if here's 30, here's also 30. That's the idea. Yep. I think although it might be difficult to kind of get started with these proofs, it's honestly really doable. And in my opinion, it was one of the most fun parts in chapter 2. So I hope you enjoyed it and great job today. And see you next time for chapter 3, looking at parallel and perpendicular lines and proofs. Bye.